Okay.
I better stay standing.
Huh?
I should stay standing there. I wander around usually, but I'll stay over here.
No. Your main audience is here.
Okay, that's
Okay, you
fine.
can just walk around.
What happened to you for this?
They have
Yeah, you randomly push my It doesn't work, you take a hammer and this works fine.
No, stop. Some time at the very beginning to make sure that the system is working. So we got ourselves a new IT, by the way. So Isaac, in addition to his PhD, now you got himself another job.
Write that on your resume right now.
Congratulations. And this was important for us because I was really pitching this talk for a long time. This could be really one of our best Kent seminars, by the way. I mean, David Hein, I'm very delighted.
It will be.
I'm very delighted to really introduce him today. In his busy schedule, really busy schedule. I mean, he's just like Professor Al-Qadi, just imagine. And he was able to find the time to come here. That's why we have it on Tuesday, not a Thursday, because that was the only time that he could come and deliver this talk to us as part of this Kent seminar. So he's going to be talking about, I mean, you hear this a lot during his presentation, permeable payments. It's, I think, one of the few innovative techniques that we use in payments, and I'm very interested, I'm really excited about this talk. And David Hein, for those who doesn't know David Hein, he is the Vice President of Applied Research Associates. He has a long experience with permeable payments, concrete asphalt payments, anything that you need to know about payments, he has the deepest experience. So I'm very pleased to introduce him today for delivering this Kent seminar. Please join me welcoming David Hein.
Thank you very much for inviting me here today. And so my background is primarily geotechnical materials engineering. I'm a structural engineer by education. I've never practiced structural engineering, so most of my work has been in pavements, be it anything you can drive on, run on, land aircraft on, and things like that. This is a little bit something different in that we have first thing they teach you in pavement engineering 101 is get the water away from the pavement structure. You know, this is something that's going to cause issues in softening materials and things like that. Well, the stormwater industry primarily is the one that are interested in permeable pavement systems. It is not something that's new. It's been around for a long time. First permeable pavement in North America was built in the early 1900s in Nova Scotia and Canada. There have been quite a wide variety of different kinds of things. Looks like concrete blocks on their side. This came from a hotel in Italy I was staying at once. All of these pavements are designed to allow water to go into the pavement instead of having it flow off the pavement structure. There are the primary pavement types of this in North America really are, you'll hear pervious concrete, porous asphalt, and permeable interlocking concrete pavements. They're basically any pavement that allows the water to go directly through the pavement structure and into the layers below. It's not like the porous asphalt that we put on top of a pavement structure that's a very thin layer. Those are things like you see in Florida where you're going driving down the highways, water goes in the top and goes out sideways. These are pavements where water is going directly through the pavement structure into the materials below, including the subgrade, and we infiltrate it if possible and basically do things to help treat the quantity and quality of water. Permeable pavements basically have a surface structure that's permeable, and all the layers underneath them are also permeable. And so what happens when water flows on top of these, and I'm just going to try and make this a little bit bigger for you, is that water flows across the top of the pavement, goes into the spaces between the paving stones in this case, or the porous asphalt or pervious concrete, ends up at the bottom of the pavement structure, and then we deal with that water through our normal design process and procedures. Porous asphalt looks like this. In the back we've got some dense graded asphalt. You see water ponding on it. In the front here we've got our porous asphalt. It looks kind of like black popcorn. It is a open graded aggregate or open graded surface layer. We take away the small portions of the aggregates, leave it very open, 25–30% voids. We sometimes put fibers and fillers in there so we get more glue to stick the aggregates together, and then ultimately all the water goes into the pavement structure. Here's a picture of a housing complex in New Hampshire. The University of New Hampshire has done a ton of work on porous asphalt pavements and water quality measurements, and you see a lot of these in subdivision roadways and pathways and whatnot all over North America now. Pervious concrete is basically the same thing. We make concrete, we make it as dense as possible to be as strong as possible, unfortunately not very permeable. So what we do is we take out the small aggregate particles from this. We basically enhance the cement by including things like fibers and fillers to make the glue stick better and be a little bit thicker to attach itself to the aggregates, and then we lay it down using a variety of different types of methods. It can be a paver, it can be an asphalt spreader, it can be a roller like this, a roller screed. You see them covering it up really quick. You want to do that because we need water in this to hydrate the cement. If the water's not in this matrix and stays there to hydrate the cement, I have no glue holding the aggregate together and the stuff's going to ravel off. And so this is very, very important when you're placing things like pervious concrete. We have additives in the concrete itself to hold water as well. If it's a hot sunny day, lots of wind out there, not a good time to be placing a pervious concrete pavement. This comes from one of the largest installations of pervious concrete in North America down in Williamsburg, Virginia. They took a big outlet mall complex, and there are no catch basins in the entire complex, the entire area. They basically removed, this used to be a stormwater pond right here. Underneath here are these big milk crates, I call them, that are big open spaces that store water. All the water from all the buildings in this entire outlet mall ends up back here with a small outlet down the back here that allows it to go into a stream behind. If it doesn't get into the ground, it goes into the stream behind there. And then we have permeable interlocking. There are varieties, tons of varieties. There's 30, 40, 50 different kinds of permeable paving stone systems. This is not permeable. The space between the stones themselves is where the water gets into it. So we've got about 90% solids and about 10% open space between these paving stones. There are some of these that are actually made from pervious concrete. You got a question? Shoot. Yep. The base is completely open as well. So we've got basically 25–30% voids in the base. And do stop me. If you got questions as we go along here, just stop me, okay? I'm more than happy to stop and answer questions. Another variation of this is from Colorado, Fort Collins, Colorado. They use a lot of these. They've got specifications actually that require all new construction, 25% of that surface must be a permeable surface. So it includes parking areas, roadways, everything else in the entire city. This comes from a brewery. They're very, very sustainable. There's no water that leaves this site. They basically infiltrate the water through this. The big beer trucks that carry the beer cases and kegs leave out through this roadway here. And so this was built probably 8 or 9 years ago, I think probably now. I've seen it quite a few times out there. And they don't also have to be concrete. These are bricks. So these are permeable brick pavements as well, clay bricks. They're also in the industry. And there's a roadway here showing you don't see any catch basins on the side of the roadway. Advantages, no trenches underneath to compact, no trenches to settle, easier to build. All the water basically from the roadway gets infiltrated into the ground, and water comes from here as well, off the top and into the pavement surface. And so we have to take care of that as part of the design, which I'll be talking about. And then there's a lot of other ones like this, grid pavements. These are the old daddy of kind of permeable pavements. Because it's green does not mean that it is permeable. All right. Under here, if we've got a little bit of topsoil and some clay soil below it, it will not infiltrate water. It's virtually impermeable. So just because you see something that's green does not mean that water can get into it. But a lot of people still use some of these systems, basically the old ways. Or even this was from out on the West Coast, out in California, in a parking lot near the Pacific Ocean. And it looks like concrete blocks kind of turned on their side. And so they filled the joints with aggregates, or the spaces with aggregates here. This is about 15% of the area of the pavement, obviously impermeable. This is what maintains it being permeable. You get stuff in here and dirt and dust and whatnot, and it reduces the permeability of these as well. And then there are hybrids and things like this. This is a grid. A company in Germany called Purus manufactures these from waste garbage bags. So all of the shopping bags and garbage bags and everything, they process this stuff and turn them into these guys. It's called EcoRaster. It is a very, very stiff grid system that locks itself together. So you could take a box of these, and all of us here, we could probably in 5 minutes cover this entire room with this stuff. Once it's connected together, you cannot get it apart. It's impossible to actually separate it. So you can drive on it, you can plow snow on it, all kinds of other things. And so this is aggregate in the middle of it that's providing permeability to it. They've got some variations on it. This is a permeable pavement with paving stone inserts. So it's an EcoRaster grid that has open spaces all around it here that is allowing water to go in, as well as the space between the pavers. And these are about this thick, and they just inset them inside these grid blocks. This is not permeable, but it's a nice hard surface to drive your vehicle on. So if you drive your vehicle over this, you're not damaging the pavement surface at all. And then there's a variety of other kind of products and epoxy-coated aggregate materials. There are actually poured in place and precast versions of this. Some guys up in Maine and Vermont are doing a precast version of this pervious concrete and just laying it on the side of the roadway, basically, to connect it up to the drainage system. And there are, again, tons of different kinds of these things that are out there. Some are better than others. Not thrilled about these kind of things because when you put the blocks together, they rub up against each other and kind of cause some of the aggregates to move up and down a little bit. Typical application of permeable pavements. This is not on a highway. These are typically parking areas, driveways, recreational trails, things like that. Parking lot is a very common use of these permeable pavers. This is from a Lowe's facility down in North Carolina near the Outer Banks. Their entire parking lot area is basically pervious concrete. And so you see a lot of these being used in places where you've got sandy soils. Soils that have a high hydraulic conductivity, water can get into the soils. And so if you put this on top, think Outer Banks sand kind of deal, no, you don't need catch basins because all the water will be infiltrated into the ground below it, which is the desire of this entire pavement system. The challenge with these are getting this down uniform, making sure it's properly compacted, making sure it's properly hydrated, or what happens is you get rattling happening. So you turn your tires like this on your car, you pop out pieces of aggregate, and that can cause some issues with it. Keys to a successful project, basically, ultimately these are not suitable for everywhere. I'm constantly dealing with landscape architects and people who say, oh, I want to put permeable pavement in here and I want it to be, subject to bus transit traffic. And I said, not a good idea. I've got a project right now in the Gordie Howe Bridge. It's a new bridge between Canada and the US up in Windsor and Detroit. And the architects sent us the plans for the parking areas and the heavy truck zones, and they're all permeable pavements because they want to be sustainable. Well, I'm the guy that says, bad idea. You shouldn't do that. So we need to look at the sites and what we have, what conditions are there to determine whether or not it makes sense or not. Then we've got two things to deal with. We got strength and we got hydraulic design. So we've got strength, we've got to be able to make the pavement thick enough to handle the loads, like any pavement design stuff. And we got hydrology, we got to figure out how to get the water in, and then what do we do with it once we get it in? Does it go into the ground? Do we have to deal with it elsewhere? Do I have to get some of it leaving the pavement structure? How do I do that? It's not rocket science. This is not really complex to do. All right? It's easy to write specifications and things, but it's new. It's new to North America, mostly probably the last 15 years or so. In Europe, they've been doing it for 40 years. But what happens in North America is I do a job in Boise, Idaho, and I see their specs. And I say, where'd you get the specs? Oh, I got it from Orlando, Florida. I went to Google, whatever porous asphalt specifications. And they just take it and they put it in a project and they want to build it there. Well, the conditions are not the same. There are really good guide specs from the industry out there. People stealing things off of Google just leads to a lot of problems after the case. Telling people that we're building a permeable pavement. I'll show you some pictures later about what happens when they don't know that there's a permeable pavement there and what it can do to the performance of that roadway. Construction inspection. I'm getting old and I'm getting really cranky when people build things improperly. I'm getting really, really angry when I see lousy construction. Well, I see a lot of lousy construction in permeable pavements because, again, they're new. People aren't knowing what they're supposed to be looking for. An inspection is not standing there and taking a ticket from a truck and saying, got 20 tons of asphalt on it. Inspection is looking at things and understanding what's wrong or what could go wrong or what kind of testing you need to do to make sure you got a high quality product. Everybody wants to be sustainable. Sustainable is a great thing. You know what you can do to be more sustainable than anybody else? Make what you got last longer. If you got a road that you're trying to have last 10 years, you make it last 12 or 14 years, that's better than anything else you can possibly put in the pavement structure and turn it into linear landfill. So making something last longer is important, and construction inspection is important for that. Ultimately, I say make the details count. I'll show you some of the situations of what happens when they don't count. This is a roadway called Alston Way in Berkeley, California, built 3 years ago now. The city really wanted to build permeable pavement because they were all trying to basically keep the waters of San Francisco Bay clean. And so that was the purpose of doing that. There are a bunch of reasons. So a couple of 3 years ago, did an NCHRP project called NCHRP, what was it, 2525 Task 82, I think it was. Bottom line, it was all water people wanting to use permeable pavements for highway shoulders. And so when I looked at this first, I thought, you guys are nuts. Like, this is a crazy thing. And so then we decided, well, what we're going to do is we're going to provide some rules and some guidance of when you can and cannot use a permeable pavement. So we came up with something like this, which is modeled after actually a matrix in the AASHTO design guide that talks about primary, secondary, and other considerations for a decision-making process. And we've listed here all the things that are important to a permeable pavement, including things like geotechnical risk, depth of water table, environmental approvals, and volumes of water and things like this. And we've taken that and turned it into a matrix. Engineers like matrices and spreadsheets and things like that. And so these are kind of telling people when they should and shouldn't do something particularly. So this is the matrix that came out of that, which was a decision tool to determine if you could consider using a permeable pavement for a highway shoulder on the side of the roadway. And so we had our primary consideration, secondary, and tertiary, and we put weighting factors on all this, and at the end of the day, it comes down and gives you a guidance here that says whether or not you can or cannot build a permeable pavement in a particular location. So it makes the engineers happy, and it's something that we can use to explain to councils and city people and designers and architects and things like that as to why this may not be the best site or why this is a good candidate for a permeable pavement structure. A little bit of a blow up of just a couple of the sides over there. We've got some weighting scale there. We've got guidance here that tells you what low, medium, and high is, and if you got a grade over 5%, it's low risk, if it, et cetera. So it basically talks about your decisions. You walk through this thing and decide whether or not it's a good idea to build a permeable pavement there or not, and then we score them all: primary, secondary, other. In this case, it came out with 65 out of or 65.6 out of 100. I think 75 was the criteria for a yes, that it works well. And it gives you an idea of whether or not you should do this or not. There's tons of guides out there about permeable pavements. There are industry guides from like the concrete industry, the paving stone industry, people like ASCE here. I'll talk a little bit more about the one later. This is from the Environmental Water Resources Institute of ASCE. Got a bunch of really good people together and came up with a really high profile manual here to give you guidance on the design, construction, and maintenance practices of permeable pavements as well. So there's lots of stuff out there to help people to understand the do's and don'ts basically of permeable pavement design. So this is the basic process. So what we're looking at here at the top is basically a design flow chart that has a structural side on the left. It has a hydrologic side on the right. The structural side is very much similar to building a conventional pavement with a few little twists in it. The hydrologic side on the other side is, in addition to making it strong, I have to make it so I can get water into the pavement and then decide what I'm going to do with it once I get there. Ideally, when you get to the bottom here, we have a pavement structure. Here's how thick it needs to be to handle the traffic, and here's how thick it needs to be to handle the water. So now it means I need thicker pavement than I need to handle the water, so maybe I want to do something to try and optimize this. The best pavement you can design is one that's just thick enough to handle the traffic, plus just thick enough to handle the water at the least cost. And that's basically our goal with designing these systems. There are a whole bunch of inputs. I won't go through them all in great detail, but the bottom line is, first thing I ask people is, why do you want to build a permeable pavement? All right, so a good example was Thompson, Manitoba. Think of up Hudson Bay, 800, it's about 1,000 kilometers north of the American border, north of Minnesota, all right? And it's a school, it's a university campus, and they want to build a permeable pavement. So I ask them, why do you want to build a permeable pavement? We want to be green. Yeah, okay, that's nice. So let me explain where you are. You are in Thompson, Manitoba. It doesn't rain here. They're in the northern winter desert kind of climate. They get this much rain a year, not even. And I said, again, why do you want to do this? Well, you know, because we want to be green. Okay, fine. You want to get LEED Silver certified? That's fine, whatever you want to do. So I said, you know, you're not going to get any water into the ground because your ground is basically sloppy, nasty clay material. So I said, it's going to take, you know, 100 years to infiltrate this much. So can you design this? Of course I can design this. So what are you going to do? Well, I'm going to dig a giant hole in the ground and I'm going to fill it full of rocks. And then I'm going to take all the water that doesn't get into the pavement, I'm going to put it in this big hole. And then it's going to be, I'll be long dead before you fill up this hole. So you've got yourself a permeable pavement that's going to last yourself, you know, 40 years or 50 years. Okay, awesome, let's do it. So we did. You know, you wonder why, but bottom line is they just wanted to be green and get LEED Silver certified points kind of thing. So I always ask people why you're going to do this. And then basically we got to look at things like the area around where we're building it. You know, do I have water coming off of a grassed area or a you know, parking area or a roof of a building or things like that? You know, how much water is going to come into my pavement structure? What do I want to do with that water? Do I want to hold on to it? If my goal is to reduce water going downstream and getting into the ground, I want to hold on to it. I want to hold on to it for as long as I can so it infiltrates the ground. Or if there's too much coming in, then I have to figure out when I want to let it go. And I can control when I want it coming in and when I want to let it go. So we look at things like storage time and time to drain within the pavement structure. If we're sending water out, what are we trying to do with it? When you drive, you got water that's moving. So if I take this bottle of water here and I put a bunch of dirt in it and I go like this, right? And it's going to be nice and brown, and I sit it here, right? Stuff's going to start falling on a solution here. You've got particles in the water. Gravity works, right? The longer I leave it sitting there and not moving, the more stuff is going to come out of solution. So I'm taking care of what's called the suspended solids, the total suspended solids are. But if this water is moving, it's always going to be dirty, right? So the whole point is to get the water to slow down and to get that suspended solids out of it. There are guidelines and rules here that talk about, they call it a thing called first flush. So when it rains, it says you got to take care of the first inch of water and do not let it leave your site. And so there are rules out there that say this. When it rains, every time it rains, the first inch of water. If it's a half an inch, you got to go all on the ground. If it's an inch of water, all on the ground. If it's an inch and a half of water, an inch got to go on the ground, and the other half we can send someplace else. So there are guidelines. Everybody's got guidelines. Everybody's got something different right now. It's driving me crazy because there's so many different kinds of guidelines from different agencies of what their goals are. There are no real central goals. Geometric details, all kinds of other things here. We want to know, you know, is it flat? Is it curved? Is it stepped? Is it a alleyway? Does it go down, you know, 5% slopes? Does it, do I need drains underneath this? You know, are there curves in it? Are there utilities that I have to deal with? All of these things are part of the geometric design and details. Is there frost? Is it cold? Is it going to heave or not, potentially? All of these things are important. And if I got something like contaminants that I'm trying to take out of the water as well. And then there's things about, well, how fast does the water go into the ground? If it's sand, like this. If it's clay, really slow. I can make it go faster in the clay if I want to by roughing it up and by making trenches and boreholes and things like that. Clogging the surface. So I've got open structure and I've got a bunch of pine trees. They're all dropping needles on the pavement surface. Are these going to eventually clog up the surface of the pavement? Well, we designed for this stuff so that doesn't affect the bottom end at the end, or the bottom at the end of the day. So basic steps here. Evaluate, can I do this? Does it make sense? 2, why am I doing this? And 3, talk about all the benefits and things like that we can potentially gain from this. Most of these are environmental, most of these are stormwater related. The bottom line is there are so many things, if we deal with stormwater at the source and not at the pollution plant side of things, you know, we're saving a ton of money. If I'm reducing the size of my stormwater ponds, if I'm reducing the amount of water that goes to a stormwater plant for treatment, you know, if I'm reducing the water sitting on the pavement surface so that, you know, you got better visibility and you got lack of water spray. There's all kinds of benefits that are associated with permeable pavements that are not pavement related, but rather water related at the end of the day. All those considerations I talked about, the primary and secondary ones, this is what we do. So this is from Berkeley, California. And so the council in Berkeley asked us to do a permeable pavement design, a demonstration project. And they said, you know, so they had us in looking at this job. And so they said, here's 8 candidates, here's 8 roadways that you have, and I want you to pick one of those 8 roadways and we're going to build our permeable pavement on it. So the matrix that I had was adapted for Berkeley, California. They have different needs and things like that at some times. And so then we went out, we looked at each of these locations where they decided they wanted to do something, and we looked at the cross sections, and these were all existing roads they wanted to turn into a permeable pavement. So they're basically rehabilitating the road, digging it up and making a permeable pavement. So we look at the areas around, what's on the sides, are there trees, are there other roads and things like this that are dragging water to the pavement surface? Tell me about what's under the ground. If I've got old utilities under the ground, probably I don't want to use them for my demonstration project, because if I got a water main break or something that happens, not a good plan. Your demonstration project's going to go up like crazy. So we come up and we look at areas and where the water's coming from, and then we look at others like this one. Took all 8 of those locations. I'm not sure if I have that. Yeah, there's the slide there. All 8 of these locations that they picked, put them through our matrix, and what do you see on the right-hand side? No, 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 can consider. They all ranked in the 40s to 60s and stuff like that. So came back and they said, why? Why is it like that? Well, because there's all of these things that are wrong, and we explained why, gave them all details. One's a major bus route, one's got tons of dirt coming in from a construction site and things like that. So ultimately, we ended up picking this guy here, Alston Way, which is near downtown Berkeley. And yeah, it's got lots of area here that dump water onto the pavement, but it had, it met all basically the rest of the criteria, giving you a relatively high rating of 81. So that's what they did. We said, okay, good, we're going to build Alston Way. This is Alston Way. We have to look at the water that falls on the roadway. These are sidewalks against the school. All the water there goes this way. All this part of the water here goes this way. And so I have to build this permeable pavement to handle all the water coming into the road from different locations. So we go and we look at this, and those are the contributing areas and stuff like that from it. And so these are the additional area. So we've got basically the pavement area, 29,000 square feet, but I've got 29,000 square feet of grass contributing water, 10,000 feet of hard surface walkways, and 6,700 square feet of other walkways, concrete walkways. I got to deal with all that water. So it's not only going to take the water that falls on it, but it's going to take all the water that comes off of it from all the other areas around it. Now, remember I said, you see grass doesn't mean it's going to basically infiltrate water. It doesn't go in. It goes off or it evaporates. That's where the water goes here. So we have 2 tracks basically. We've got a structural track and we've got a hydrologic track here. Talk a little bit about the structural track. We need to get water into the pavement. So we need to do something and use a permeable surface. In this particular case, it's paving stones. The spaces between are getting water to go in, and so I need to make sure I can get water in. On the structural track, I need to basically come up with a structural design, which I'll go through a little more detail a little bit further on. In order to determine if we can get water in, if we can get water in, by testing other pavements, we know what the permeability is. I've got a project that's going to start up in a couple of weeks. I've got a manufacturer of paving stones who's building about 10 foot by 10 foot square areas of 8 or 9 different kinds of his permeable paving stones, and then we're going to do testing like this infiltration test, this permeability test, where we're literally just putting plumber's putty and a known, it's an ASTM standard. There's one for concrete, there's one for that's concrete, that's paving stones, and you're basically dumping water in and timing it and finding out how fast the permeability is. Something like that guy there, the permeability of that will be something like this much water an hour. So you're talking like 4 feet of permeability in an hour going down into the ground. It doesn't rain that much. All right, the highest rainstorms you get in a 100-year storm in the U.S. are roughly 12 to 14 inches of rain in 24 hours, not in an hour. So these are massively permeable. If you don't have things like this, we go and build stuff in the lab. So we go build a permeable pavement system in the lab. We basically pour water on the top. We simulate clogging by getting grad students to dump dirt on there with toothbrushes and work it into the joints and stuff like that, all those wonderful jobs you get to have in a university. And this is at a university actually too, just so you know that. So we build those and then we do permeability tests and we find out what the permeability of these materials are, and we look at the change in permeability over time. So as I try to clog it, it goes from say 200 inches an hour down to 190, 180, and usually they end up like it will clog like this, it's kind of like this, and it goes asymptotically flatter around about 90% loss of permeability, so around 10% of the 200 inches I started with. So in the next 25 years, I expect to lose permeability. That's okay, I designed for this, I get 20 inches an hour, that's way more than I need for the biggest design storm in North America, so that's not an issue. We look at what the permeability is going through aggregate materials and stuff like that. So I do a mixed design. People here have done some work in mixed designs in asphalt and concrete. Well, we can change our mixed design. All right, this is one of the things that people don't do and they need to do more. Why do I want to have a really massively open aggregate structure when I only get 4 inches of rain a year? I'm in Lubbock, Texas, I do a different mixed design than if I'm in Houston, Texas. All right, and so we changed the mixed design. I can give up some permeability to get more structural capacity out of the material, get a higher modulus of the material, and it makes more sense. It's going to last longer. So it's a kind of give and take relationship here a little bit. Hydrologic design, water goes in, water goes out. So water comes down from precipitation here, obviously. We get water coming from areas around it, you know, the parking lot and the park we saw there. Some water evaporates, some runs off the surface potentially. A lot of it hopefully goes into our pavement structure. If we get it into the ground, that's really good. If we can't get it into the ground, then at some point the water builds up here and we need to get rid of it. We don't want it coming out and filling up over top of the entire pavement. So we want to get rid of it, or we want to control it, let's just say. Most agencies specify that when you get water in the permeable pavement, that you can only keep it for 24 to 72 hours. They don't want water sitting someplace where you may have mosquitoes and things like that potentially growing, and ultimately you want it to flush out of the pavement structure. You're delaying it by 72 hours is huge when it comes to storm events and water downstream and things like that. So that's the basic goal from this. The permeable pavement design and how we do that, we build it up of different layers. We have stuff that looks like railway ballast, that's our sub-base. We have some like 25 or inch minus material, that's your base. And then whatever you put on top, your asphalt, your concrete, your pavers, etc. We call this the reservoir course because it's where we hold water. This has porosity of 35–40%, or let's call it 33%. That means I can hold 4 inches of water with every 12 inches of aggregate I put in. So it's 33% air voids. That means I can fill it up and I can do that. Ultimately, we need to know about the ground, the subgrade soils. How fast can I get water in here? If it's raining on here and it comes to here, what do I do with it? How fast can I get it into the ground? If it's sand, like this. If it's silt, slower. If it's clay, it's going to take a long time to get into the ground. So we have 3 basic kinds of designs. We have what's called full infiltration. Full infiltration, no. I'm just not going to answer that. The phone's ringing. It's okay. Don't worry about it. It'll stop. Anyway, so we get full infiltration. This means we're trying to get water into the ground. All the water that goes in the top has to go into the ground. This word I absolutely hate as an engineer, when the architects want an uncompacted soil. What do you do when you're building a pavement? Beat the crap out of the subgrade so that we can make it work. I don't know how to hang up on this thing, but hang up. Ignore. Oh, that was obvious. Need an engineer with a PhD to show me this, eh? I know. I know. Sorry, man. So if you see this word, cringe, big time, because uncompacted soil makes me very, very nervous. You know, if you've got a really lousy soil like a clay and you can't get water into it, and somebody says, oh, we'll just fluff it up. I've seen specifications say, take a bucket and fluff it up. No, not in my world, okay? If you got lousy clay, beat the crap out of it, make it as strong as possible because I want the pavement to last. You can build infiltration trenches. You can do holes. You can do that big hole I talked about up in Thompson, Manitoba and things like that to make it work. So there's no need for this kind of stuff. Full infiltration design, those are just the formulas of water stuff, and I'm not going to go through that stuff. There's a new standard coming out from ASCE. I've been the chair of this committee for 4 years now, and we're finally going to get into the last steps of issuing a design standard to the public, which has all of this stuff and details in it. So it's basic water analysis, looking at the total volume of water, where it's coming from, how it's getting there, and then making sure that we don't leave it in the ground too long. The ASCE standard has all of this detailed examples and stuff like this of how to calculate it as well. Then we have what's called partial infiltration. Partial infiltration basically is where the water goes in, we get some going into the ground, but it doesn't all go in, it can't all go in. And so if water builds up, at some point in time we want to take it out, all right? Usually we don't bury this guy in the aggregate, we bury this guy in the subgrade, and then to control the height, I turn the pipe up and I leave the outlet higher. So it builds up until it gets to the outlet height, and then eventually it comes out of the pavement structure. So this is a little bit more detail. I'll show you a couple of pictures of that a little bit later. Then so the partial infiltration design, same kind of thing. It's about water balance and where the water's going and how much water we store here. At what time do you actually let it go into the pipe and leave the pavement structure? I said I don't do it here. We usually put the pipes down here so they don't have to. If you do it in the middle of the aggregate and construction, you got a chance of damaging the pipe. So we don't want to do that. And then we've got a no infiltration design. This is a popular one used in places like brownfield sites, so areas where this is contaminated and I don't want water in. Texas, Oklahoma, places where I want to, the soils are very susceptible to moisture changes, and so they will actually heave based on moisture changes. Or just quite frankly, if you want to save the water and use it to water the plants. And so a lot of people will do these designs because they're into water capture. So you'll basically capture the water in the pavement. Usually you'll have a cistern and a pump in it downstream so that you can basically pump the water out and use it to feed the grass and the plants and all that kind of stuff. So brown water reuse. And it needs a drain to get there. So it needs some way to get to the cistern and things like that. So this is the no infiltration design. And the equations are pretty simple for a no infiltration design as well. So again, I won't go through the details with respect to time and whatnot. So then what you got to do is now we say, okay, that's fine. So I know how to do the calculation of water, where it goes in and out. I need to still come to do structural design, but we do things like defining the area of our permeable pavement, what size it is, and then we look at all the contributing areas, those three areas, the park, the concrete sidewalk, the other sidewalk, and we look at, well, if this is my contributing, or the hallway is my contributing area, how much water is going to land there? What kind of surface is it? Is it rough or is it smooth? Is it got a slope on it? How long is it going to take for it to come through that door and get onto my permeable pavement? So I need a water balance, right? And so I do that for grass is different than asphalt, is different than concrete, that's different than trees and all the rest of this stuff. And so this is a computer program developed by the Interlocking Concrete Pavement Institute folks that basically allows simplistic permeable pavement design for architects and whatnot. Water comes from all kinds of sources. So it comes from, this is out in Portland, Oregon. It's a Rock Creek campus. It's a college campus out there. And I took this picture a day after it rained. Water is still coming off the grass and onto the permeable pavement structure. So we usually model for 24 hours up to 48 to kind of maybe sometimes 72. They can come from things like sprinklers. They can come from roof drains. This is dumping water on top of the permeable pavement structure from the roof drains. And we look at things like drainage. This is the stormwater patterns in stormwater, how water gets to when it falls out of the sky, how it gets to your surface. This is showing you percentage of rain over a 24-hour period. The dark red line is most of North America. So Champaign here would be it. It would start raining, it would rain slowly. After about 8 hours, you got 10% of the rain occurs. Then all of a sudden you get a major storm, it just dumps rain on you in 40–50% of it happens in 30 minutes, and then it slows down at the other end. This is more like Seattle, where it kind of rains slowly and it keeps raining and raining. I need to know this because I need to know if I can get water into the pavement structure. So we usually simulate this at tenth of an hour intervals or whatever, at 6-minute intervals, something like that. So we got a water balance happening on a continuous basis. And this is a really simple, like $100 program that they've sold 5,000 or 6,000 copies of this basically to architects who use it to design structural and hydrologic designs. And then we basically calculate how much water is in how much rain comes down, how much is inflow into the pavement structure, what comes from the catchment area, this stuff here, to give you a total inflow, and then we model the water. How much water gets in over time, 5-year storm, 100-year storm. And it gives you 24-hour total cubic feet, cubic meters kind of deal. Then we go through and do a whole bunch of other things. We look at how much water builds up in the base with time. So this is showing you how much water is in there for a 5-year storm or a 2-year storm up to a 100-year storm. It's going to be about 5 inches deep in the pavement structure. These are subdrain pipes. So subdrain pipes we put them at certain elevations to take water out at certain times. When it's like this, it means all the pipes are running full tilt. All the water is full in the pipes kind of thing. And so these are basically some hydrologic tools to do that. And then there's not just the drainage that happens in the pavement and out of the pavement. We call supplementary surface drainage, things like cuts in the curb here. If water's coming so heavy it can't get into here, it will actually go through there and into here. This is a really, really good site because this is that Rock Creek campus in Portland. Back here, this is all, parking area is all asphalt dense and permeable pavers. All of this area here drains down here. And this right there is this. And then there's a stormwater pond here. So the water has to infiltrate here. If it can't, it goes here, infiltrate here, it can't get there, it goes down here, tries to get into the ground, can't get into the ground, ends up in this one pipe, goes down this ditch here. Plants now are like this tall and they all suck water and use water up. And then at the end here, it goes into the stormwater pond if there's water in that ditch. I've been out there a half a dozen times over the years. I do a lot of stuff in Oregon. And I've never seen water in that stormwater pond yet. It's grass green, dry, so that's a really neat stage design to allow all the water that gets onto that site basically to infiltrate into the ground. So nothing actually leaves the site. So they've got a set of tennis courts right here on the back here, and they really could have actually made another set of tennis courts there. Because there's no water going into that pond ever in the last 7 or 8 years. And so again, more land use, better land use, and it's going to have a financial benefit to people. This is from Tennessee, this is Franklin, Tennessee. My sister-in-law lives there, and I was at the bank. So it's one of these banks, you know, pull through, drive through banks and whatnot. And so they've got permeable pavers all around it, and they've got basically supplementary drainage here. They've actually got a chair you can sit on here, and water basically gets in. If it can't find a place to go, it goes to the lowest spot, that little drain down there. I've never seen two of these the same. Not two permeable pavement sections in any project myself the same at all. Here's one from England, the UK. Entire subdivision, not a single catch basin in the subdivision. All of the driveways, all of the parking areas are permeable. All of the roadways are actually regular asphalt, and this is their urban stormwater pond. So I was taking pictures of this. A lady comes out of her house. She says, you know, what are you doing? And I'm explaining, I'm taking pictures of this. She says, well, let me tell you, it's a wonderful thing because, you know, all the water doesn't come in. And I said, I found this really amazing. You got this, yeah, when they first built it, there was no thing around, no fence around it. And we thought it was bad for the kids, so they made them put a fence up. And I said, lady, have you ever seen water in here? She goes, no, I've been living here 20 years, never seen water once. So I said, obviously your thing here doesn't get used much often, right? And the developers were awesomely happy because they got to build, he told me, 8 more houses on this site because they dealt with all the water. You know, and the roads, you know, no bumps and trenches and things like that. It was absolutely amazing. So, quick version of the structural design. Most of you have probably seen AASHTO structural design stuff, not far from down the street in Ottawa, Illinois, done years ago. There are 2 methods here that we're going to show you. One is first the AASHTO method. Basically just heavy vehicles. Your cars mean nothing to pavement design. We don't care about motorcycles and cars, they're irrelevant. We care about these guys and these guys, these big guys. We basically take those, turn them into easels, equivalent single axle loads, plug them into the AASHTO design equations, and calculate easels. So this software allows you to say, is it a roadway or a parking area? If it's a parking area, pick one. Cars and light trucks, cars and occasional heavy vehicles. It'll tell you how many easels the design is for and do a design. If you say it's a roadway, it'll give you this. You know, tell me about the design life and the AEDT, the traffic amounts, and how many days a year do you have traffic on it, comes with this. Calculates easels. This was released in 2010. When this thing hits 600,000, a yellow flag comes up over here under traffic and says that's a lot of traffic for a permeable pavement. When it hits 1 million, it shuts itself off. It won't let you design a permeable pavement for more than 1 million easels. So that's a limitation. Back in 2010, that was deemed to be good practice. The Brits now design for 10 million easels, and I quite frankly believe you can design one for any level of traffic at all, provided you know what you're doing. But again, these are mostly architects that do this, and we know architects don't know anything about engineering really, even though they take engineering classes, and so we need something to guide them to say, don't be stupid, right? That's the whole point of this. We need to know about the resilient modulus of the ground, the stiffness of the ground. Well, if it's wet, I need to know how long is it going to be wet? Because wet is bad. You know, my CBR just went down to 3 or 2 because I got a wet subgrade all the time and it's crappy clay. And so we need to know stuff about that. We need to know all kinds of things and how we get resilient modulus. I mean, bottom line is that it's resilient modulus. All the designs are resilient modulus. There's no design really that goes through a CBR and stuff like that. It's all converted or came from resilient modulus in the first place. So basically, just a couple of inputs on here on how to get that value. And then it's a straight AASHTO design that says, give me a structural number, what's required, what are you going to give me in terms of pavement structure, calculate the layer coefficients times the thickness values. If you're used to doing this kind of design stuff, you'll know that paving layer, asphalt, concrete, pavers, whatever, usually is 0.42-ish. It's discounted because we have basically normal paving stones, in this case of paving stones. Normal paving stones have got sand in the joints. When you put the sand in, it's about 2-3 millimeters in thickness. You put them together, you pack the crap out of them, and I can't do this. I can't move the paving stones. It's like 2 pieces of sandpaper on each other. To make that permeable, I have to open up the joint. All right? So I make the joint wider. And I put little bars on the paving stones so it keeps them wider. Then in that joint, I put aggregate, 3/8 inch stone chips. I can't put sand in. Sand's not going to be permeable enough for me, so I put chips in there. The chips don't give you the same shear friction that you would when you have sand particles touching each other. And so we lose some strength of the pavers. Same thing with the asphalt and the concrete. They're not the same strength because we got open graded aggregate making up that strength. And then the layers below them, they're also open graded aggregates, and so they also may have different values associated with them. So AASHTO designs. AASHTO is like the simplest design on the planet. It can teach you how to do that in 15 minutes. The rest of the world thinks it's pretty funny that we do pavement designs using the AASHTO method, right? Everybody's using stress strain and all the rest of the stuff. AASHTO is like, you do what? Like, seriously? No, we haven't done that since ever, you know? And so, same thing with the paving stone industry. Said, hey guys, we want to know something about that 1 million easels thing. Can we build pavements with more than 1 million easels? So, obviously, it was not far from accelerated load equipment here. This is UC Davis out in California. They got the Cement Association of Nevada and California and some of the guys together, and basically said, okay, we're making this ASCE standard. And we'd like to do something more mechanistic than simple, oh gee, let's use some layer, layer coefficients times its thickness. And so a couple of years ago, went out and built some pavement sections out there, different thicknesses of base and sub-base, and basically did accelerated testing, back and forth over that. Looked at primary modes of failure. In this case, with paving stones, it is rutting. The paving stones themselves are very high strength, 8,000 PSI concrete. You know how hard this is for me to speak in PSI, by the way? You should appreciate this because I'm a metric guy, all right? So I'm doing this for you, okay? So, and we would have, an inch of rutting, 25 millimeters, okay? And so we tested them dry and wet, and miraculously, when you've got a bunch of paving stones together with a bunch of big coarse aggregate with lots of friction, when it's dry, it doesn't go anywhere. You've got lots of support around there, and so it's really interesting to look at the science and the difference of the aggregate base and sub-base because that's where all my strength comes from. I don't want to use much asphalt or concrete if I have a choice, and so this is a different mechanism. I don't have good shear capacity in the open graded aggregates, like a bunch of little aggregates touching each other like this. And what happens when you push them? It's actually funny because you see like springy action too when you watch trucks drive across them. It's kind of cool. So anyway, test it, dry, wet, come up with a model basically that says this is what happens when you do dry for 18 inches, 26 inches, and whatever that is in Yankee units. And then we have, I hope there's no Southerners in the room here, because when I say that, they get really pissed off when I say Yankee units. We're not Yankees! All right, so we measured the rutting. But then we basically developed rut models for all of this, and because this was done in conjunction with the ASCE design standard that we're coming out of here, use the normal methodologies to look at stresses and strains and accumulations, et cetera, to come up with rutting. And they built this design tool you can Google this and download this thing and use it for permeable pavement design if you wish. But I'm designing a standard for the masses. So giving them this, they're not pavement guys, right? They want something that's simple for them to use. So we basically took that whole thing and we turned it into basically a simplistic design process. So we make you pick basically how much traffic you have, what your subgrade modulus is. We want to look at something like the contributing area drainage ratio. We want to look at how many days the ground is wet, et cetera. And so we go out and we look at data from NOAA's websites, et cetera, like that. We find out how many days a year when you've got potential for having wet subgrade. We also decide we want to determine if there's what the infiltration capacity of the subgrade is. If the water's going in and going right into the ground, then I really don't care. It's not wet as far as I'm concerned. So we look at the drainage capacity here. We look at the number of days of year where we have precipitation of more than 12.5 millimeters in this case, and what is the total percentage of occurrences of those days during 365 days a year. So we calculate 28 days of standing water sitting on the subgrade. We take that data, we plug it into this guy. We plug in the traffic data, we plug in the number of days of standing water, and then we've calculated, based on the resilient modulus of the subgrade, we've calculated for people what the subbase thickness needs to be. Permeable pavements, basically three kind of things. Pervious concrete will be somewhere probably between 5 or 4 and more 5 and let's say 7 inches in thickness, maybe 8. Asphalt layers usually no more than sometimes 2, but up to probably 5 inches in thickness. Pavers are always pretty much the same. They all come in only metric. They're 8 centimeters, 80 millimeter pavers, and so we know that. And then they all get put on top of a granular base, about this thick, 4 inches thick. So the only thing we need to know is how thick a subbase do I need to handle the strength, the load. So this is basically a subbase table. Higher traffic levels, more subbase needed. Higher number of days that are wet, more subbase needed. Different subgrade strengths, more subbase needed, et cetera. So these are the design tables that are in our standard that you'll see coming out, I said, in probably a couple of months or so. In terms of structural design, I mentioned already, honestly, you can design permeable pavements for anything. So the story with this guy, this is the Battle Command Center in Colorado Springs, Colorado. So I got a phone call from a local consultant. The Army Corps of Engineers are building this Battle Command Center. Basically, it's a place where they got guys coming together to work, to train, and all this kind of stuff. The Pentagon says that they're all new infrastructure needs to be designed to be LEED Silver certifiable. So by sustainability standards, you got to be LEED Silver certifiable, and 25% has to be certified. So they want everything green. So these guys looking at this Battle Command Center says, well, how can we be green here? It's Colorado. Colorado's got not a lot of water, but they're a very green bunch of people. So let's build the main pavement area in front of the command center to be all permeable pavement. So that's fine. So I get hired to do this. Design a pavement structure, no problem, send this thing in. Then they come back and say, well, you know what? It's not a big enough area, so we're going to actually design this entire, almost like a parade ground area. We're going to design it all permeable pavements, and we want you to design it so that we can put our tents out there, and we want to take tent spikes and we want to pound them through the pavement structure. Okay, so I said, then you're going to go pavers, because you're not going to put a hole in the concrete, a hole in the asphalt. So I said, you're going to go pavers. And he goes, okay, and I'm going to give you pavers that have holes that are about that wide in the corners, in these individual little corners here, so you can ram your spike in there. Okay, cool. Oh, but we want you to make sure they can handle these Bradley vehicles. And I said, what's a Bradley vehicle? Guy sends me a picture. It's got a tire about that tall. Can you do it? Yeah, okay, we can do this. How many Bradley vehicles are you going to get? So whatever, do my design, calculate, fine. I'm in Dallas, Texas. I get a phone call from the guy in Colorado. He says, Dave, we got a change in your pavement structure. He says, we need to change it again. I said, what? And he goes, well, we want to design it so that we can handle M1A1 Abrams battle tanks. I said, you want to drive tanks on my permeable pavement? Yes. Can you do it? Damned if I know. I said, but I sure as hell ain't stamping that drawing, I'll tell you that. That's not going to happen. So he says, well, what do you need to do? I said, well, we can design something. I said, but I'm not putting my name on it unless I know that it's going to work, kind of thing. So I said, we're going to build a test section. And he says, okay, let's build a test section. So design it for me. So we designed this thing. This is my test section at the Battle Command Center in Colorado. And so we got a bunch of tanks out there. You can't hear the noise probably. All right. Bye. I know how to turn you off. Oh, not yet. Doesn't want to go off. All right. So anyway, this is the tank driving around on the top of this permeable pavement. There are, you'll see some things on the surface that are looks like it's carrying something up. It's actually the rubber on the bottom of these tank treads. This stuff here comes off the tank tread. It's actually carrying it off the bottom of the tank tread. And then somewhere back here, they put in these spikes that are about that diameter, solid metal, and he drove over them and went like this. And then when they drove over them, he goes, okay, so now how are you going to fix that? One of the contractor comes out, he pulls it out of the hole, kicks some of the stone back in, so here you go, it's fixed. So he loved it. And this guy came in with his tank. He came driving in, hit the brakes. The gun goes like this down, almost hit the front of it. I went, oh my God, the concrete was around here, cracked. Oh, there, right there, see the spikes? Here and here? He drove over them, bent them 90 degrees, and then we pulled them out, and everything was fine. And then what you're not hearing here is a whole bunch of old Army Corps of Engineers giggling. Because they're going, that's awesome, look at this thing. And they're laughing like hell. And so here he's going to drive over one of the fence spikes. So anyway, like I said, you can design these things for it, but I wouldn't get your normal geotech guy to go and touch this kind of thing. You need somebody who knows something about permeable pavement stuff. Let's see if I have several videos of it, so I'm not sure. Oh yeah, there you go. Watch him, he's going to drive over that spike. Crunch, bent it in half, and the guy went out and picked it up later and took it up. So it can be done, is the bottom line there. This was from a bad experience at the Olympic Village in Vancouver where they were making a mess. All right, I'm running out of time here. So some other things we need to deal with, all right? When I went to university, I was really good at water. Stormwater, water management, anything to do with water. All my courses where I'm getting 95, 96, 97, never worked in water my whole life, And so now all of a sudden I get to work with water guys. And this is cool. I can actually use something I learned back in university many, many, many years ago. So this is an outlet pipe from the pavement structure going through a weir that's going to dictate how high the water needs to get before water will be allowed to get out of the pavement structure. And so that's just a kind of a typical detail. Slopes, we put berms inside of slopes. So we do this a lot in alleyways behind like Richmond, Virginia, Chicago, all over Boise, Idaho. A lot of alleyways are made from permeable pavers because you don't want to be digging down. There's nothing to put the water into. There's no storm sewer down there, anything like that. So they use them as a conveyance method to get from A to B. And so they're basically not trying to get water in here so much as to control it and take it somewhere. So we basically put in geotextile liners under this, and water goes down. We put a hole in there, we let water go through slowly, at another little hole there, a bleed hole. And an entire neighborhood in Atlanta was done like this 2 years ago, and it completely eliminated flooding in the neighborhood. So all the pavements in every roadway in Atlanta have been done like this. I invited the engineer actually to our last conference in Houston last year when he came and showed this to people of how much valuable it was to the community. Stuff coming off of roof drains, another detail for that. Not really a great idea, quite frankly. A lot of people want to do this. Where was it? Another city in Colorado, Longmont, Colorado. I designed one that had 30 times the ratio of surface area impermeable to permeable. All the water in all the buildings downtown went into the drain pipes and then went into the permeable pavement structure. That's pushing it limit quite a bit, and we don't want things coming off the roof like sand from shingles and this kind of nasty stuff. So you really don't want that to go into your permeable pavement. If you've got something like this, it can go down there. You can do the traps and all that kind of stuff here too, but it's not desirable. We had this in our standard. We had a ballot vote on this a month ago, and we decided to remove it. We're not putting it in the standard at all, saying it works, but it's not great design practice. Being beside buildings, you don't want water going into foundations and stuff like that, so we've got a cutoff here to prevent water in the permeable pavement from getting back underneath the building foundations. Transitions between other pavements types, dense graded to open graded and things like that. You don't want water going from your permeable pavement into the one adjacent to it. Use of geotextiles and things like that. Here's the design. I said we don't put it up into the aggregate. We put it down in the subgrade, the drain. And then you may have a geomembrane, you may have a geotextile, adjacent to things like curbs or buildings and even the soil down here potentially as well. So this is a detail that comes from that software program. Once you design it, you can say hit AutoCAD and it will send you an AutoCAD drawing of your pavement design. And I won't go through all this. This is all about geotextiles and the thicknesses and things like that of what you need. So a bit of things to learn a little bit differently. Test results, this is basically just parroting back things like permeability and porosity and structural coefficients of layers and whatnot. Again, I won't bother with that. And then we look at what's it good for? Is it satisfying my storage capacity, my storage goals, my infiltration capacity, my rainfall intensity, et cetera? And so people have different goals. And so I just show that just to give you an example of, this pavement works for everything up to a 5-year design and it's not working for this. That may be important to you, it may not be at the end of the day. And so this is our output again, different design storms, different infiltration, different water going into the ground and stuff like that. This thing lets you walk through and design a permeable pavement right through from A to B, A to Z at the end of the day. Subgrade considerations, you don't run your construction equipment like crazy over top of this and compact it if you're trying not to compact it. Infiltration is necessary to measure infiltration. We need to know what it's going to be like in a greenfield site. If we're out this is the middle of Berkeley, California, we dug a test pit in the existing roadway and did infiltration testing at the elevation of where our new pavement was going to be. So double ring infiltrometer test here. This is the actual results of Berkeley. 94% of all the water that landed on that roadway or came through that roadway never came out the other end. So we had a 94% success rate in removing water from the pavement structure. 94% success infiltrating it into the ground. All of the water from that site eventually ends up in one catch basin that we have on the adjacent street. We wanted to monitor it for quality and quantity, and we haven't been able to get any water worth beans out of it to basically measure, to test for quality of water, because it's all gone. So that's the ultimate in quality improvement as well, ideally, because it's not going into the storm drain system. A little bit about construction. This is the construction site at Berkeley again. This is our sub-base. They didn't know about some gas mains in here, so we had to change it and use some cellular confinement stuff, but ultimately we built the pavement structure. Sub-base looks like railway ballast. Base looks like 1-inch minus material. Chip material, these two go in asphalt and concrete. This goes in the permeable pavers as well. That's the chip that goes underneath as a bedding layer and also in the joints. Installing and doing base testing, if you ever see anybody that says go out and get 95% standard Proctor maximum dry density, tell them they're stupid. You can't do that, all right? Because it's not really, you can't put a nuclear density gauge and stick a probe into open graded aggregates and get anything that's meaningful. It's a waste of time. And so usually it's done by a test strip method. So you basically go back and forth, you measure density, you could use a back scatter on a nuclear gauge, or we specify how big the equipment needs to be, and then you can do a test strip kind of thing. Usually this has become very much more popular in using for compaction assessment, so LWD, lightweight deflectometer. The thing that pisses me off about this, I was telling one of the other students earlier about, we're talking about FWDs, falling weight deflectometers, and I said the first one that I owned was serial number 4. The 4th one ever produced on the planet was mine. So I've had a lot of experience with this. When I saw that back in the 80s, all right, a long time ago, I said, you know what? We need a portable version of this thing so we can take this to Africa and all kinds of other places. And I wanted this built 40 years ago. And it took like 25 years before anybody started doing that, which was crazy. Found great success with this. This is what's in our standard. We wrote the spec for the compaction testing in our standard based on the LWD as well. Porous asphalt installation, the big thing about this one is getting it at the right temperature to get it compacted properly. This goes against dense graded asphalt. We want it to be as dense as possible to get the to make it the strongest it can be. So ultimately we want to make sure this is relatively strong as well, but the temperature is really important. Concrete, we need to get it built, and the cement hydrated so we get decent concrete. This is from a parking lot across from my office in Toronto. Covering it up really fast. This is a floor spreader that's used to construct the surface, and you can lay it with big machines as well. So this is a larger machine. Pavers, they have these devices here that can pick up a square yard of pavers. They could complete this entire room here probably in 20 minutes, and we'd be finished basically laying these things down. So there's clamp systems that pick them up and lay them down on the pavements. This guy's basically just spreading aggregate into the pavers and compacting it to give it its shear capacity. This is a parking lot for a liquor store down in North Carolina. Yeah, I was the guy taking the picture. This is in Omaha, Nebraska, Zorinsky. It's a park area kind of thing. Underneath here are these guys. So when the water gets in here, can't get into the ground here, goes into here and ends up in these pipes out down the trench in the back here. Walkways, go down to Colorado Springs, you'll see lots of this. Trees love this. I've always been asking the botanists and whatever the arborists if they like permeable pavements, and they absolutely love them because they're open spaces. The roots go into the open spaces. It doesn't lift the sidewalks. Also, they've got access to water, so they're really happy. The canopies in Berkeley are bigger than, and there's another one actually for you too, Hassan, is the improvement in the canopy of the trees resulting in better oxygen production that's another good one. Yeah, we've come up with a couple of new ones today. Roadways, that's a roadway out in New Hampshire. Nice thing about it, no water spray. Although the water basically gets sucked into the pores here. It's quieter too, quieter to drive on. Roadway shoulders, Caltrans is doing this, or wanting to do some of these construction, build them beside the road. Heavy vehicles, that's one from the UK, doing some test sections. This is from my NCHRP project, so it's like, how would you actually build a permeable shoulder on a roadway? And we came up with several different methods of doing that. How would you do it in an urban section versus a rural section? So again, just a few details. A little bit of maintenance and I'm done. So a little bit of maintenance. This was that place out in Portland, Oregon, where I said I was there before they opened it to traffic. And so I'm walking around taking pictures of the permeable pavement, and the landscape guys came in. Landscape guys came in, they dumped all this subgrade or the topsoil here, picked it up, and we're planting the trees. And so I'm taking pictures of this, and the guy says, "Oh, you know something about this? That's a funny looking pavement." I explained what a permeable pavement was, and he goes, "Yeah, it's probably not a good thing for it, right?" So the landscape guy's dumping dirt in the middle of the pavement. So I said, "No, that's, didn't somebody tell you about what this thing was?" No, I didn't know anything about it. That's at the Russian River Valley out in California. I drove by that, and of course I turned my car around. My wife said, "Now what? Another permeable pavement?" Yeah, I got to go take a picture. And so this was somebody else was doing some maintenance basically and putting a tarp down and putting the junk on top of the tarp, which was really good. What we don't want is things getting into the joints and growing. This is from Davis, California, a pervious concrete pavement. All these leaves and stuff basically ending up clogging the permeable pavement. And when you see water on top of one, that's just bad news. So that's not a good plan. That's a really old one too, though, I know. And then this is my Olympic Village job up in the Olympic Village in Vancouver. I was brought into this job because the supplier was unhappy about what they were going to do. I reviewed what they said. I gave them a report that says, "You guys are nuts, man. Don't do this." And then I walked away because they wanted to hire me, and I said, no, you're not going to listen to me. So I said, I don't want to have my name associated with a failure. Eventually then they called me and they said, what are your terms? First time in my life I had a client ask me what my terms were. So one of my engineers sitting in front of me, and he says, don't do it. I know you're going to don't do this. I said, it's the Olympics, man, I got to do this. So I gave him the terms. Terms were I needed 3 weeks to review and change all of their designs. 2, I wanted to have, what else was it? I wanted to work directly for the city, and 3, I wanted to have one of my people on site during construction. Disaster, complete disaster. From day one, basically, they started screwing stuff up there. So underneath there is a permeable pavement, right? I said, it's a permeable pavement, no dirt, no water, no heavy trucks, no nothing. That's what they did. I said, really cool. Well, where's the permeable pavement here? Right, this is during construction. I wrote we wrote hundreds and hundreds of defect notices. And then after the Olympics, I went back and we did a punch list thing for what had to be fixed. I stopped at 300 items. I said, guys, this is ridiculous. Just rip it up, start over again. It was so bad. So yeah, people don't listen. That's okay. If they listened, I wouldn't have a job. So I'm okay with that. Sucking the stuff out. You can actually suck the stuff out of the permeable pavements if they get clogged. You can use things like this. There's a thing called a true vacuum suction device. Works better on pavers than it does on asphalt or concrete because this has less voids in the surface, so it can get a decent vacuum in it. And then winter maintenance is just like anything else. Really cool. I was at Fort Collins we did a demonstration project on winter maintenance to show people, and it snowed that day. And when it snowed, it was really neat because the heat from the earth below is warmer. It comes up through the joints and actually melts the pavement faster than it melts a regular pavement. So that was kind of neat. This is our standard, our ASCE standard coming out. This consists of a committee of about 23, 24 people, half water people, half pavement people. We've been arguing with each other for a long time. And it's really interesting to sit in a room and you have the pavement people arguing about the pavement design, right? And we all argue and argue and argue, and then okay, we're gonna do this, and then all of the guys from water are laughing at us going, you guys don't know what you're doing, do you? And then the water people do the same thing and they talk about their stuff, and I'm going, what is this orifice equation and stuff? And then it's like, you don't know what you're doing either. And yet we all came together and we're writing a national standard, ANSI accredited standard. So just remember where some of these standards came from. Some of it's engineering opinion. This is where we are. We've got a ballot finished. 45 days it goes to the public. It's coming up shortly, and then mid-2017 we're going to publish this. So that pretty much takes care of the permeable pavement stuff. And since we started late and I talk long, we don't have a heck of a lot of time, I think, but